Now we will study the final topic of this course, modeling the two-dimensional two-energy group hexagonal multi-assembly reactors. The objectives are constructing a hexagon reactor, applying boundary condition and PDE coefficient, calculating the K effective and the normalization assembly powers. The only difference between the hexagon reactor modeling and the rectangular reactor modeling is the geometry. While applying boundary condition, PDE coefficient, and post-processing are quite similar with the rectangular reactor modeling. In addition, you need to learn how to cut the reactor to 1/12 or 1/6 to take the advantage of the symmetry. So a hexagon reactor is a reactor core composed of multiple hexagon field lattice. This figure shows the Russian VVER 440 hexagon core configuration. And on the right, these two figures shows the flux distribution of both energy groups calculated by MATLAB. For this particular problem, you will see that this geometry exhibits the symmetry for 1/12 of the core. Therefore, to model this reactor, we only need to model 1/12 of this core. The red figure shows a sample complete hexagon array. And all the hexagon elements are regular hexagon with the exact same dimensions. So all the lattice will have the same size. The center row will have odd elements. For this problem, the center row has 7 columns or 7 elements. It should be an odd number. Therefore, at the center of this array, it will be the core center. In addition, the number of elements of the row above the center row or below the center row, the number of elements will be reduced by 1. For example, this row, it has 6 elements, which is 7 minus 1, you get 6 elements. And the row below this one will also be 6 elements as well. Then moving forward, you get 5 elements, then 4 elements. The total number of rows, it will be equal to the total number of columns in the center row. For this one, we have a total of 7 rows, and we have a total of 7 columns in the center row as well. Okay, so the number of rows is equal to the number of columns in the center row, and they are both odd number. Moreover, some elements at the corner may be removed to make the entire core to look like a round shape. Let's take this VVER core configuration as an example. You can see that there are some few elements that are removed at this corner, so that this entire reactor configuration will look like a round shape. And it means that sometimes you will see that there are some field assembly that is missing at the corner. Okay, this is normal. This slide shows some important relationship among adjacent lattices. It is very important to know how to calculate the coordinate of each hexagon lattice. There are 2 variables used to describe the size of the hexagon lattice. One is the pitch P. The pitch P is defined as the center-to-center distance of 2 adjacent hexagon lattice. This is P, this is also P. and this is also P. So as shown in this figure, the center to center distance of any two lattices, any two adjacent lattices, is P. This pitch P is also equal to the lattice flat surface to another flat surface distance, as shown in the figure. For example, the distance between this surface and this surface is also P. And the distance between the center of a lattice, to any flat surface, from the center to this flat surface, is P over 2, okay, 1/2 of the P. Therefore, along the x direction, each lattice is shifted by P centimeter. For example, this lattice is shifted from this lattice to the right for P centimeter. In addition, that is along the x direction. Along the y direction, each lattice is shifted by square root of 3 times P over 2. For example, the distance between this center to this center is P times square root of 3 over 2. You can verify this from some simple geometric formula. So this is the pitch. Another one is the side length. We use the A to denote the side length of a lattice. So this is side length A, and all the side lengths are equal to each other. The side length is also equal to the distance between the hexagon center and its vertices. From here to here is also A. Okay, from here to there is A. Here to here is also A. So the problem may give you either the A or the P to describe the lattice size. And the P and the A has this relationship. So the pitch P is equal to A times square root of 3. Based on simple analytic geometry knowledge, if you know the center coordinate, in this case x0 and y0, you can calculate the coordinate vertices using those formula. And a hexagon can be drawn using the polygon shape that adjusts the coordinates. For example, the first vertex, its coordinate will be x0 plus a cosine 30, and the y coordinate is y0 plus a times sine 30. Then go to the next vertex, the angle will be changed to 90 degrees, and so on. I will provide a MATLAB script to automatically draw a hexagon at your convenience, so you don't have to draw the hexagon by yourself and perform this tedious coordinate calculation. The hexagon core may exhibit many different types of symmetry. 30-degree or 1/12 of the core and 60-degree or 1/6 of the core are common. As shown by this figure, this will be 30 degrees of the core, that is 1/12 of the core. This is 60 degrees of the core, and it is 1/6 of the core. This is another type of 60-degree cutting. Again, it is 1/6 of the core. So just pay attention that there may be different cut patterns for each symmetry. Some uncommon symmetry include 90 degree. This is 90 degree or 1/4 of the core. And also 180 degree or 1/2 of the core. For example, you may model the top half or the right half. So based on the actual geometry, we just need to model a piece of the core to save the computation time. Now we will demonstrate one example to show how to model a hexagon core. So this problem is modified from the 2D IAEA benchmark problem. For square lattice PWR, we have modeled that problem as your homework. This core has 13 field assemblies across the core diameter. As shown in this figure, and this figure only shows 1/12 of the core. Therefore, this is the center row, and it only shows the right half of this center row. So you have 7 assemblies, and this one is the center assembly. So you have 6 assembly to your right, and another 6 assembly to your left. So the total is 13 field assemblies in the center row. And the core is 1/12 core reflective symmetry. So we only need to model 1/12 of the core. The field assembly pitch is 20 cm. It's shown here that is flat surface to another flat surface that is 20 cm, which is also the pitch. The reflector is not included in the core, and the boundary condition and the core boundary is specified by albedo boundary condition. So we have two albedo boundary condition. One is albedo factor 0.125, another one is 0.5. So we need to calculate this problem twice for different boundary condition. So 2 different albedo were used for 2 cases. So we have 2 cases corresponding to realistic and vacuum boundary condition. The table gives the nuclear parameter data for the IAEA core, and this one is your cross section. Okay, cross section. The table gives the cross section for this core, and this figure gives the eigenvalue and the power density reference solution for the 2 boundary conditions. So we have the reference solution, and our result should match those values. For example, this is the K eigenvalue, this is the K effective. And the power, normalized power is shown here. So this one is the assembly power for albedo 0.125. And this power is for albedo 0.5. And this the first integer is the material index. So this is material number 1, and material number 2, and material number 3. In this case, material number 4 is not used. And next, we will demonstrate how to solve this problem using MATLAB. First, make sure that the PM hex is in your working folder. Here, the 00 is the center coordinate of this hexagon. The second input is the side length of this hexagon. And the last one is the rotation angle in degrees. The PDE modeler will automatically open. We need to adjust the access limit in order to view this entire geometry. You need to estimate the total size of your core so that later you can see the entire core. Then we need to duplicate the assembly in the first row. First, we select P1 and Ctrl-C, then Ctrl-V. Each assembly is shifted to the right for 20 cm. So we enter 20 for the X displacement, 0 for Y displacement. There are 6 more assemblies need to be created. Now we will generate the first element in each row. The X displacement will be 1.5 pitch, which will be 20 times 1.5. The Y displacement, as shown in this figure, it will be pitch times square root of 3 over 2. There are 3 rows above the center row. Now we have all the first element generated, and we are going to follow this core configuration to create the remaining elements in each row. For example, for the row above the center row, we have 4 more repeats. Now we have all the hexagon units, and we need to use a rectangular to cover the bottom unwanted region. We need to adjust the rectangle coordinate. This coordinate is not unique. As long as this rectangle is able to entirely cover the unwanted region, that would be enough. The top edge should overlap the x-axis. Next, we are going to draw a polygon, a triangle, to cover the unwanted region along the diagonal line. We first roughly draw this triangle, then we adjust the coordinate. You need to know how to calculate those coordinates. This diagonal line is very critical. It must exactly overlap. This y is equal to tangent 30 times x. Okay, the x is 10, so the y will be 10 over square root of 3. Make sure that you click the tab and make sure you see that the coordinate has been changed to the value you have entered. You must use the square root of 3 to represent this value. Do not use any float number to approximate that. Here we choose x value that is large enough. Then if x is 120, then the y will be 120 over square root of 3. This one, the x must be -10, and the y can be any value that is high enough. So we enter 70. Press tab. Press OK. Then we adjust the set formula. We use the bracket to enclose all the hexagon, and minus the rectangle 1 and minus the polygon 17. Then we go to the mesh mode to check the mesh quality. We want to make sure that the mesh quality is good and there's no very tiny meshes at a certain corner. If you see that, you have to go back to your draw mode and fix your geometry. Here we use the edge size of 2 cm to generate this mesh. And from this figure, you can see that the mesh quality is good and all the meshes have the similar size. Then we change it to the generic system. You can change this one at any time before boundary condition and PD coefficient. We select all the edges and change it to Newman boundary condition and all 0. We change everything to reflective boundary condition. Then we hold your Shift key and select all the external edges. Then we change it to the albedo boundary condition. It's Newman, and Q11 and Q22 will be the albedo factor, which will be 0.5 for the first case. We are going to calculate. Then we go to the PD mode. We need to select all the regions first and change everything at the same time. So select the Eigen mode because most of the region are of material type 2. Therefore, we are going to change everything to material type 2 first. We will follow the formula and enter those cross sections. C11 is D1, C22 is D2. A11 is sigma A1 plus sigma S. This value is already given in the table, so we don't have to calculate that. A21 is negative sigma S. And A22 is sigma A2. D11 is the mu sigma F1. D22 is mu sigma F2. Press OK. Now we need to select all the boundary assemblies and change it to material number 1. Then we select these 3 regions and fill these 3 regions with material number 3. Then adjust the eigenvalue search range to from 0 to 2. Then we can solve the problem. This is the first group neutron flux distribution. We change it to jet for the color map. Change it to V to show the second group neutron flux distribution. Check the height and set both to V so that we can pop the second group neutron flux 3D view. We can do the same thing for the first group neutron flux 3D view. So the color and the height are set to U at the same time. Then we export the solution and the meshes to the MATLAB workspace and go to the MATLAB to write our script. First, we need to calculate and display the K. The K is equal to 1 over L1. We can also display our relative error because we know the true value from the reference. So the percentage error for our multiplication factor can be calculated in this way. So relative error is our result minus the reference value over the reference value. So you can see that our K effective relative error is lower than 0.02%, which is very good. Next, we calculate the normalized assembly power. First, we need to define our assembly map. Following this figure, we need to restore this array to the full array. The center row has 13 columns in the real model. Therefore, each row will have 13 columns. We restore this core to the full model in order to make sure that our center assembly is located at the center in this array. So this is the center row. If the assembly is outside our 112's core, we just use 0 to represent that empty assembly. The lower half are all 0. Pay attention how this array is organized. Next, we calculate the side lines. This is the fission cross-section. If the sigma f is given, then we use the sigma f. If the sigma f is not given, then we use the mu sigma f. When you enter the PD coefficient, we always use the mu sigma f. Make sure that the PDE tool power hex is in your folder. In this function, the PTU is from your solution. The hex array, we just defined this one in line 4. 0, 0 is your center hexagon coordinate, which is 0, 0. Then side lines is calculated, cross-section is also defined. And this variable is the total number of field elements inside this core. For this problem, all the assemblies are field assembly. And you can see that from this figure, we have 6 full assembly and 9 half assembly in the center row and also along the diagonal line. For the center lattice, only 1/12 of that center lattice is included inside this 1/12 of the core. And therefore, we add that 1/12. We do a test run, and we can see all those values. Next, we need to multiply the assembly power by 2 in the center row. the center row is located in the fourth row in the hexagon array. Therefore, that is 4, comma, column, multiplied by 2. We also need to multiply the assembly power by 2 along the diagonal line. And we are going to use a loop to do this job. We will loop from the first row to the fourth row. So for I row from 1 to 4. So the first one is the row index. Then will be the column index. So in the first row, that number 1 is located in the 10th element. Okay, 10th element. Therefore, we use 11 minus 0. So 11 minus 1, so that is 10. Then, when this I row is moved to the second row, it will be the I row is 2, and that 3 assembly number 3 will be located in the column number 9. Last, we need to adjust the power at the center assembly. The center assembly is located at row 4 and columns 7. This row 4 and column 7 assembly should be multiplied by 12. We already multiplied by 2 when we adjust the center row. We multiplied another 2 when we adjust the diagonal line. Therefore, we just need to multiply another 3 so that 2 by 2 by 3 will be 12. Then we display this power array. So this will be our final result, and those values will be the normalized assembly power for each assembly in the figure. Next, we go back to our PDE modeler and save this model to a new file. In order to calculate the case 2 for the albedo factor that is 0.125. Go to the boundary mode and select all the external boundaries. Then we change this Q11 and Q22 to be 0.125 so that we get another case. Everything else will be the same. Then we solve it. So this is our group 1 neutron flux. and we export the solution and export the mesh. This will overwrite our previous PTU. Then we can run this script again, so everything will be the same, except we need to change the reference key. We change the reference key to another value listed in the reference. Save as this one to another file. Then we run it. This is the final result for the albedo value that is equal to 0.125. This will conclude the demonstration. To draw your first hexagon, make sure that this file is located in your MATLAB working folder. So pmhex.m. This one is included in the zip file provided at the Blackboard. At the MATLAB command window, you just type pmhex. This one is the center of your hexagon, and we are going to place the center lattice at the origin. Therefore, this one will be bracket 0, 0. And the second variable is side length. The unit will be centimeter. And the rotation angle. If you enter 0 for this rotation, it will draw a vertical hexagon. Then you press enter, it will automatically open the PDE modeler and draw this hexagon. In the MATLAB command window, you can enter this line to draw a hexagon like this. So the 0, 0 means that the hexagon center is located at the origin. Certainly, you can move it to another location by changing this coordinate. The 20 over square root of 3 is the side length of this hexagon, because we know that the pitch is 20 centimeter, and the side length is calculated as A is equal to pitch over square root of 3. So from now on, for all this square root of 3, make sure you enter sqrt bracket 3 to get the most accurate value. Do not use any other float number, otherwise your program will most likely crash. 0 means no rotation, and by default, if you have 0 rotation, then it will give you a hexagon like this. So we can call it a vertical hexagon. And for this course, this value is always 0. And the PDE Toolbox will automatically be launched. And you can adjust the axis limit to show this hexagon. Again, you need to estimate what is your size of this core, okay, in order to show the entire core. Next, we need to analyze this model. We know that the core has 1/12 symmetry. Therefore, we are going to model this part of the reactor, so that is 30 degrees. And we need to construct the core as shown in this figure. We need to construct all those hexagon lattice, and then we are going to cut it in order to remove the unwanted region and form a core exactly between 0 degree and 30 degree. In addition, all the coordinates must be precise. First, we are going to produce the first row. we are going to select the center hexagon, the first hexagon you have created. Then press Ctrl C and Ctrl V. Then you will get the dialog like this. We need to enter 20 as the x displacement because, as shown by this figure, each lattice is shifted to the right for 20 cm. So shifted to one pitch. So x displacement is 20, and the y displacement is 0 because we are producing one row. In the first row, in the bottom row, we have 7 assemblies, and we already have the first one produced. Then you need to enter 6 as the repeats so that it will produce all these 6 assemblies. Then we are going to produce the hexagon, the first hexagon in each row, like this one, and also this one. Again, we copy the center hexagon and by pressing Ctrl C, then press Ctrl V to get another paste dialog. In this case, the x displacement will be 1.5 pitch. For example, here, this is 1 pitch, and here you have another half pitch. So from this center to this line will be 1.5 pitch. Okay, 1.5 pitch. It means that this one is moved from here to the right for 1.5 pitch. This is along the x direction. So that's 20, which is the pitch, times 1.5. And for the y displacement, that is the distance between here and here, okay, between here and here. And as shown by the previous figure, this value is p times square root of 3 over 2. So we use 20 times square root of 3 divided by 2. So we have a total of 4 rows. The bottom row is already produced. Then we need to produce 3 more rows. Therefore, number of repeats will be 3. Then repeat this process to produce the remaining lattice in each row. For example, here you need to produce 4 lattice. Here you need to produce another 2 lattice. Pay attention that you should always use square root of 3, and you should not replace the square root of 3 by any float number. Otherwise, this approximation will cause a small overlapping or a gap between 2 assemblies, and that will cause some strange error. Now you should have a hexagon array like this figure. And the next step is to cut the unwanted region. The first step is to draw a rectangle and cut the bottom part. So you are going to draw a rectangle and cover the lower half of your bottom row. This is only the sample coordinate. As long as this rectangular is large enough to cover all this region, that is enough. Next, we need to draw a triangle in order to cut the diagonal line. This line is very important. It must pass through the origin. In this case, it passes through the origin, and also pass this point exactly. You can calculate the starting point and also end point. And the size of this triangle should be big enough, so the coordinates are not unique. As long as this triangle is big enough to cover this full half hexagon, then that is enough. I'm not going to explain the detail how to calculate those coordinates, just simple analytic geometry knowledge. And the set formula should also be changed. We need to use the bracket to enclose all the hexagon. P1 to P16, they are the hexagon, then everything is union. Then minus this rectangle minus this triangle. So that the result will be this part. Okay, result will be this part. After you have defined your geometry, I would recommend you go to the mesh mode to check the mesh quality in order to ensure that your geometry is correct before going to the boundary condition and the PDE coefficient. Because once you change the geometry, you have to redo everything again. Therefore, we want to make sure that your geometry is completely correct. The default mesh will be coarse, and you can adjust the mesh edge size, and to get the quality mesh, the mesh should have a similar size. They should not have a very tiny meshes around some corner. In that case, your geometry is wrong. You have to go back and check your geometry and fix that. For boundary condition, this line is reflective boundary. This line is also reflective boundary because these two edges, they are symmetric axes. The external boundary is set to albedo boundary condition. For the albedo boundary condition, we choose the Newman, and we set the Q11 and Q22 as alpha. Q1 and Q2 as alpha. Previously, for vacuum boundary condition, the Q11 and Q22 are set to 0.46922. For the albedo boundary condition, you just simply replace that value by this alpha, which is the albedo factor, which will be provided to you. Next, we need to go to the PDE mode. Remember that we need to set all the subdomains together as the first step. For this model, most of the assembly are of type 2. Therefore, we are going to set everything to type 2 first. Also, pay attention that sigma A1 plus sigma S is already given as a single value. Therefore, we just need to enter this value as the A11. That will be enough. Next, we need to select all these external assemblies and set it to material number 1. The final step for PDE coefficient is the material 3. So you just need to select these 3 regions and change those values to material 3 cross section. Then change the eigenvalue search range to 0 and 2. Then you can proceed to solve this problem. This slide shows the neutron flux profile. The left column is the group 1 neutron flux distribution. The right column is the group 2 neutron flux distribution. At this moment, I believe you are quite familiar about how to draw these neutron flux figures. Next, you need to export the solution and the meshes to MATLAB workspace. First, we are going to calculate and display the K effective. K is equal to 1 over L1. Then we calculate the assembly power. The calculation procedure is similar to the rectangular. First, you define this hexagon array. We are modeling 1/12 of the core, and we need to restore this hexagon array to the full array, so that the center of this hexagon array is located at the center of this entire array you are entered. So this actual reactor will contain 13 assemblies at the center row. Therefore, we should have 13 entries, and the center will be this 3. Okay. Then we have 3 rows above and 3 rows below. Okay, 3 rows above, 3 rows below. The actual core will be this part. However, to make this matrix to be a rectangular matrix, so we need to include those zeros. We do not need to enter additional rows because they are not modeled here. Although you can do so by enter more rows with zeros. Then the pitch is 20, and hexagon side length will be 20 over square root of 3. The cross section will be mu sigma f1 for material 1, mu sigma f2 for material 2. Then semicolon to break the first row, then the material 2, then material 3. Next is assembly power. We use this function, which is also provided to you. The first 3 variable will be PTU, will always be this. Then this variable will be your hexagon array, defined here. Then this 0, 0 is the center coordinate, will be the coordinate here. Hexagon side length is calculated here, and the cross section is defined here. Next one is the total number of fill element inside your geometry. So you can count the full assembly will be 6. The full assembly are marked here. So this has 6 full fill assemblies. For this particular case, all the assemblies contain fills. All the assembly contain fill. So all the assembly are fill. However, for other cases, if an assembly is not fill, then you should not count that assembly. So we have 6 full assembly. We should also have several half assembly. At the bottom, they are all the half assembly. And this one, and this one are also half assembly. So you can count. There are 6 in the bottom row and 3 along the diagonal line. So that we have a total of 9 half assembly. Okay, 9 half assembly. The last one is the center assembly. The center assembly will only include this small triangle, that is 1/12 of this center assembly. Therefore, we have the last 1/12. This will calculate the total assemblies included inside your 1/12 of the core. Next, we need to adjust the assembly power, because some of the assembly, only half of them are included. So the half assembly include the bottom row or the fourth row. So 1, 2, 3, 4. This is the fourth row. So all the fourth row are doubled. So assembly power of the fourth row will be doubled. Then we will double the assembly power along the diagonal line. Okay, along the diagonal line here. So we use a loop. So it will loop from the row 1 until row 4. Okay, from row 1 until row 4. So this assembly, the assembly in the first row is the number 10 assembly. So you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is number 10. Therefore, the first one is number 10. So we use the 11 minus the row number. So the first row is 1, so 11 minus 1, you got a 10. And when this loop go to the second row, so you have the row 2 and column 9. And this one will be the column 9. So it will fix this one, this one, this one, and also this one. And all those assembly power will be multiplied by 2. Last will be the center assembly. Center assembly should be multiplied by 12. However, we have already multiplied this value by 2 when we adjust the center row. We also multiplied the center assembly by another 2 when we adjust the diagonal line. Therefore, we already multiplied by 4. Therefore, we just need to multiply another 3 so that we will multiply this center assembly by 12. Finally, we display all those power. We display the assembly power. This slide shows the final result. We have the K calculated as this value. We can compare this K with the reference solution. For albedo is equal to 0.5. You can see that our result will be quite similar to this one. And our normalized assembly power should match the bottom value in the publication. For example, the top one will be very close to this one, and everything should be lower than 1% relative error. We can also compare this one to this one, or compare this one to this one, and everything should be precise. You can save your model to another file and only change the external boundary condition, only change the boundary condition along this line, and change it to the case 1 albedo factor, which is alpha equal to 0.125. Then rerun the simulation and rerun your post-processing script to get the solution. This is the calculation result for case 1, whose albedo factor is equal to 0.125. You can compare this K with this value and compare your normalized power with those values. Next, we will model a 60-degree hexagon reactor. I will not provide the MATLAB demonstration, but I will summarize the major steps. And your assignment is to practice this problem again and to see if you can get the same result as shown in this slide. So this model has the same lattice size. The pitch is 20 cm as well, and we will reuse this IEA PWR problem cross-section. In this case, we are going to have 4 different materials. So we have material 1, 2, 3, and also material number 4. Recall that if the sigma f is if the efficient cross-section is all 0, then this material number 4 is not filled. Therefore, when you count the number of filled elements inside your model, you should not count material number 4. The albedo boundary condition 0.25 is applied to the external boundary, and this one is reflective, and this one is also reflective. This figure shows the draw mode. You need to generate all those hexagon assemblies. When you generate those hexagon assemblies, you need to learn how to enter and when to enter the negative displacement. For example, when you generate those assemblies, you need to enter the negative for the y. And draw another two two triangles. Draw these two triangles to cover the upper diagonal line and also the lower diagonal line. Do not forget to adjust your set formula. The union of all the hexagon minus two triangle. Then go to the mesh mode to check your geometry. Make sure that the mesh quality is good and there's no very tiny meshes around a certain corner. Then adjust the eigenvalue search range and solve the problem. So we have the first group neutron flux and the second group neutron flux. Next is the MATLAB script. For this MATLAB script, we need to enter the material map of both the upper triangle and also the lower triangle, so that this core will contain this part. So the actual core will be this part. Then we will move to the assembly power. Here we have a 17 full assembly. When you count the full assembly, do not count the assembly number 4 because it is not filled. And we have a 6 half assembly. Okay, so 3 along the bottom diagonal line and 3 along the upper diagonal line. The center assembly is covered by 1/6, so we enter 1/6, so that this formula will calculate the total number of field assembly included inside your 1/6 of the core. Next, we will fix the assembly power along the diagonal line. So we are going to correct the assembly power for the row 1, 2, 3 and row 5, 6, and 7. Therefore, we just use one loop to loop from 1, 2, 3. Okay, 1, 2, 3. And here we will also correct the assembly power in the bottom half of this core. For example, when row number is equal to 1, we are going to fix this one, so that is 7. Then row number is 2, then we are going to fix the row number 6. When we correct the diagonal line assembly power, we didn't touch the center lattice. So the center lattice should be multiplied by 6. So we use another line to multiply this assembly power by 6. Then we display this assembly power. This slice shows the final result with the K and the normalized assembly power. You can compare your value with the values on this slice. You should get a similar result. And now this topic and the entire course is completed.